And to kind of preview this and to try to get you guys to notice, let's use this graph that I had up here that is supposed to, it's a little dated, okay, but it still is a good graph, but it's supposed to show how the number of people that sort of subscribe to the internet, in other words, that basically got internet access, how it changed in those 10 years. Again, I know this is dated. When I see 1995, I think of high school graduation. When you guys see 1995, I don't know, what do you think of? A time that didn't exist, maybe. But look at how internet subscribers changed. Okay, every one of you should say that it kept increasing. Okay, what you mean by that is that the slope is positive. And so I guess what we're kind of saying here is that you already know this. You look at that graph and you say, everywhere along that graph, the slope is positive. Again, that's because it keeps going up. But you should look at it and say that something seems to be different about the way it's going up. Should I say for the first 5 years and then maybe like the second 5 years? Do you agree? It's not like increasing the same way. And what you're starting to notice there is, as I sometimes forget, here's another statement. Remember, f prime of x just means the slope. And when we say f prime of x is greater than 0, that's just a fancy way to say the slope is positive. But back to the thing that's different. In that first 5 years, there seems to be something different about the way the graph is increasing. And what's happening is that it keeps getting faster. When I say it keeps getting faster, I mean the slope keeps getting faster. Do you see like a tilted line? Do you realize that the tilted line, as you move along that blue region, keeps tilting more and more? It keeps getting steeper. That means that the slope is increasing. Now, you can look at this and you can kind of say, yeah, okay, the slope is increasing. Or you can really process it and realize that when I say the slope is increasing, what that means is that the tilt of the line, again, keeps getting bigger. The tilt of the line keeps increasing. Compared to that interval, right? Like those second 5 years. It's supposed to kind of stand out as really obvious that there's something different right there. And what's different is that the slope keeps getting smaller. We would say that the slope is decreasing. Okay, what that means is that the tilted tangent line is getting flatter and flatter. Now, before we go any further, you got to understand that the statement we made at the beginning, that is that the slope is positive, the beginning statement, is true in both of these regions. But to say the blue region, the slope is increasing, compared to the red region where the slope is decreasing, those are two separate ideas. Okay, so this is going to require a different analysis of the derivative. By the way, the spot in the middle, and it's not so much by the way, but the spot in the middle is called the inflection point. Now that's a new idea, but an inflection point is a place where you get this change of slope from increasing to decreasing. We're going to keep processing this, and I know as a fact that students have to process what I'm really trying to say here. In other words, what it means to be an increasing slope or a decreasing slope. But to say it a little easier, like an easier way to say it, is to describe that blue region as concave up. Now, this is going to be language that we use. Does it make sense? Does it look like the graph is cupping up? To say it's concave up means that it's cupping up. Again, the curve of the graph. Compared to this region, that's concave down. It's cupping down. It's curving down. So these words concave up and concave down will match with this idea of the slope increasing or the slope decreasing. There's one more thing I want to put into this graph. Can we squeeze something else in here? It has to do with the derivative. It actually has to do with the second derivative. Can you guess what we're going to say about the second derivative? It's a new place that we're going to go. But what do you think would be true about the second derivative? In the blue region, it would be, let me show you, positive. F double prime will be greater than 0. It's going to lend itself to another number line. So if you're kind of like, what's positive? Well, literally like the numbers that you'll get from that second derivative, like a number line. I'll show you, but I think you'll catch on. You'll be ready to make the connection. But the second derivative is positive when it's concave up, and then, as I'm sure you can guess, the second derivative is negative when it's concave down. Maybe you remember back on the first day, we had a graph over here. And sometimes it's helpful to go back to that graph and understand that the stuff that we just talked about internet subscribers is also true for this. Okay, and I'm going to use this graph when I give you kind of these summary screens. This kind of has it all together. And maybe you already wrote something down. Maybe you want to still write this down. But this kind of puts it all together in one place. A function is concave up if the slope, if the derivative is increasing. A function is concave up if the slope is increasing, which means the second derivative, f double prime, is greater than 0. Listen, that's a loaded statement, okay? At some point in your brain, you have to like process, okay, this is what he's saying. Now, I think it's pretty easy to process that concave up just means that it's opening up. If you look at that blue region just visually, it's opening up, concave up. But to say that the slope is increasing and to really understand what the teacher's saying is to understand this. I did this before on purpose, so this would be like the second time you've seen this. But everywhere in this blue region, the slope of my line is in a state of increase, which means it keeps getting bigger. Here it's really negative. Here it's less negative. Obviously it's going to be 0, but now it's positive. Now it's really positive. When I say the slope is increasing, I'm talking about this. I'm talking about the tilt of this line. Okay, and that's the same thing as concave up, which is also the same thing as double prime greater than 0, which we'll do on a number line. It's kind of just the opposite of everything. It's probably a good idea to write it down. Do you understand what it means? concave down. We don't use the phrase or the word convex. It's all concave. So it's either concave up or concave down. Again, concave down, orange region. It's like opening down. It's like cupping down. The curve, the cup, it's called concavity. If the derivative is decreasing. Now, there's going to be a time where I put words like this on a test. And I'm not big on memorizing if we don't have to. I'd rather you understand. I'd rather you visualize what it means for a derivative to be decreasing. It means this thing. Do you already see it? Okay, it's in a state of decrease. As I move along here in this orange region, the tilt of this line keeps getting smaller and smaller. Basically, it keeps getting more negative. Okay, so the slope is decreasing. It means concave down. It also means double prime is less than 0. That's not a bad graph to jot down or refer back to the first time we jotted it down at the beginning of the chapter. Inflection point. Yeah, inflection point. The place where all this changes. This is kind of like this is the new critical point. I mean that. This is actually the new critical point. As you guys will realize, it's the critical point of the second derivative. In fact, that's what this other statement is. It's the critical point of the second derivative. It's when double prime is equal to 0. It's when double prime is undefined. As you're going to find out in a moment, it's everything that we already did. You're just going to do it with f double prime. Okay, and let's go through kind of like one problem. This is good. It's always good to see this on the first day, especially if I don't see you for a couple days. You have this kind of live version to reference, where we're going to completely analyze a function now for the works. The works would be when we're able to not only come up with extrema, not only come up with increasing, decreasing, but now come up with concavity. Okay, so let's have at it. I want to make sure I get the right thing here. Everything's good. We got x cubed minus 12x minus 5. And the directions in my words would say, let's analyze it for the works. Okay, and you're going to find out that that takes us down the same path that we've been on. You actually need to still do the derivative, the first derivative. And again, according to the quiz that I handed back to you, most of you are doing this really well. If you have some mistakes, keep learning. Because you always set the derivative equal to 0. That's where you find those critical, first derivative critical points. And of course, when you solve this, you eventually end up with x squared equaling 4, which means that x will equal plus or minus 2. Now, those are pretty important numbers. In fact, they're so important that they end up on a number line. It's a derivative number line. I'm going to label it this time. But we put plus or minus 2 on our number line. Okay, now remember, in each one of these intervals, that is to the right of 2, that is between the 2's, and to the left of negative 2. In each one of these intervals, we have a certain type of slope. We don't know until we plug these yellow numbers back into the derivative what kind of slope we're going to get. Okay, you can do this with a little just in your head. You can do this on a calculator. I would say this type of problem is no calculator worthy eventually. So just realize what I'm doing. I'm plugging in right here. So it's 3 times negative 3 squared minus 12. As I'm trying to teach you guys to do, you really just need to look at that and decide if it's positive or negative. I think it's 27 minus 12. You don't even have to finish the math to know that that's going to be positive. We'll plug in 0. We'll plug in 3. Of course, plugging in 0 is pretty easy. And plugging in 3 is actually the same as plugging in negative 3. But we're going to plug it in right here. When you plug in 0, you get negative 12, negative. When you plug in 3, you get 15 again, but it's positive. Now, those plus and minus signs refer to the slope. I'm going to do something because I want you to do it also. I want you to realize that this still holds the keys to most of this problem. This right here reveals most of the problem. Okay, this whole thing about inflection points, it's kind of like the icing. It's kind of like a final touch. But right now, 100% the graph goes up. Right now, 100% the graph goes down. And it goes back up. I want you to be able to do the same thing. I want you to picture the graph based on the slope, because that's the main idea. But I also want you to add this second derivative, this concavity analysis. And of course, I want you to understand how it all goes together. So let us continue doing the derivative. How you doing? Just a derivative of 3x squared? Derivative of minus 12 disappears. Now, we're going to do the same thing. We're going to find the critical points of the second derivative. You mean set it equal to 0? Mm-hmm. Solve that. Yep. This critical point has the potential, notice I say potential, to be the inflection point. I should have mentioned that these critical points have the potential to be extrema. Now, the reason I keep saying potential is because ultimately you have to go to the number line to decide if it really is a change point. I should have said this about these extrema. Okay, it's pretty clear that they're max and mins. But I want you to understand that this critical point has a different destiny. It's to be the inflection point. But we don't know if it's the inflection point until we do the second derivative number line. Okay, now the second derivative number line, it's kind of its own thing. Try not to even worry about what happened up here, although they are connected eventually. But right now, I can just do my thing and plug in a couple numbers on each side of that critical point. Where are we plugging them in? Right here. Okay, we're plugging them into 6x. I'm going to show it, even though it's kind of easy, just to make sure that if you look back at your notes, you know what you were doing. So we plug in -1. Obviously, we get a negative answer. We plug in +1, and we get a positive answer. But you got to look at this plus and minus. I'm talking about this plus and minus. You got to look at this a little differently. But here's the connection. It's already happening in my function. What's already happening? Concave down, concave down. Everywhere to the left of 0. Okay, so that's good. Concave up, everywhere to the right of 0. It's kind of like the concavity's always been there, but now we officially analyze it. Now we connect it. And now we say that this is an inflection point. It's an inflection point because it's switched concavity. Just like these were max and mins, because it's switched the type of slope. So what's kind of our final answer? Well, it's not so much the final answer, it's realizing what we just did here. We drew the original function, we identified its max and mins, that is its extrema. We have the increasing, decreasing, and now we're going to add this idea of concavity. I guess, if there is a final answer, it's this list. It's this list. Let's put inflection first, since that kind of came before the concavity. Are you realizing that I'm really just adding a few more statements to our box of answers? Obviously, the bottom statements. We still have our max and mins based on the first derivative. We still have our increasing based on the first derivative. Just by the way, it probably wouldn't have been a bad idea to list these answers before I colored this graph for the concavity, because please understand that when I say negative infinity to negative 2, I'm referring to a different section of this graph. I'm referring to the original section that was going up. And when I say 2 to infinity, I'm referring to that section. So the blue and orange sections, they don't relate necessarily to my increasing, decreasing. But obviously the blue and orange sections do relate to my concavity. Okay, x equals 0 is the inflection point. X equals 0, that's what we found here. And then again, as we've said a couple times, it's concave up for the orange section, 0 to infinity, concave down for the blue section. I switched the colors. That's kind of, I didn't want to do that. I switched the colors from our two graphs. But the answers are right over here. There is kind of one thing that I'm leaving out, sort of that annoying piece. I know it's kind of annoying, but to get the y value of our 3 points, plug back into the original equation. It's easy to plug 0 in, gives you negative 5. Plugging in plus or minus 2, maybe the teacher will just tell you that comes out to be 11 and negative 21. Look, you might be looking at this and saying, do I have to do all that work? Well, this was like a standard problem. Everything kind of behaved like you thought it would. Everything switched, okay? Everything had a certain concavity, but not every problem's like this. So the analysis we went through, the number lines that we went through, basically the next lesson or the next piece of this lesson is to figure out what if it's kind of abnormal? How can we still use these concepts? So the answer is you want to do this, okay, even though maybe you kind of feel like that you already knew that was going to happen. But that's what we'll do next, okay? All right, well, we'll see you whenever we see you.